So I can go over a very brief mathematical problem, how GAs would work. So you have a simple function here of two variables, x and y. It's supposed to minimize this within this interval, right? So x is negative 5 and 5. And y is between negative 5 and 5. Okay? So what is the first step that we take? You have to have a way of binary encoding these variables, right? So let's say x is constrained to lie between x lower and x upper, like this. But our random variables, so our design variables, we had negative 5 and 5. So we now select how many bits we use to encode the solution. We can use 5 bits, we can use 10 bits, we can use 20 bits. More bits that we have, more resolution we have in us, right? So here I just showed the example of 5 bits. You go from the lowest number is called, let's say, 0, 0, 0, 0, 0, and then the largest in that interval is assigned 1, 1, 1, 1, 1. Okay. So we look for bijection means that you should always be able to go from a number here to, of course, you discretize, but you should always be able to go back to the decimal form. And whenever you have the decimal solution, you should be able to go back to the binary representation. And the number of bits determines fineness. So if you are using 6 bits, of course, then the numbers will be closer. Okay. Because the x lower and x upper remains the same, you're basically partitioning this into much finer intervals. And so the number of those will be 2 to the n bits minus 1. Okay, number of those intervals. Okay, so length of one interval is given by this. That's how we know the length of one interval. So as you go from one binary representation within that reasonable space to the next one, this is how far you will move in decimal. And we can just use basic calculations to go from one to the other. And mind you, so the numbers are from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. And we have to convert it to the actual x values, which may not start at 0, right? So you have to move this sequence so that 0, 0, 0, 0 is assigned to x lower, right? So that's all the calculations that you see here. Nothing fancy going on. Okay.
So, like, what will come in place of this decimal value of the string?
In the GA?
Like a numerical value will be there, right?
If you have, first we'll take the numerical value, okay? But then we will assign to it a binary code. And then GA will only work with binary code.
Okay.
And then you have to have a way of coming back to the binary code, which you will use something like this, right? So binary code first will convert that into a number, right? But the number will be from 0 to whatever 2 to the n number is. And then we again transpose it back to whatever the constraints were. Constraints don't have to start at 0. In this case, it's negative 5 to 5, right? So that's why we have negative 5 plus decimal value of the string times the length of one interval. So that tells you how many steps you have to move to get the actual decimal number. So you write these codes so that you can convert from one to the other. Okay. How do we set number of bits assigned to each variable determines the resolution? And here's some example again. So like we just use 2 bits, okay? Just to clarify what the point that you're making. That binary would be 0, 0, 0, 1, 1, 0, and 1, 1. If you just convert it directly to decimal, you get 0, 1, 2, 3, right? That's direct. But then now you can transpose it to, or rather map it to the interval negative 5 to 5. So there's only 4 points possible, negative 5, negative 1.666, positive 1.666, and 5. If you look at the the difference were you moving in steps of 3.333. That's pretty coarse, right? We're only looking at 4 points. And it's 3.333 because it's 1 over 2 to the 2 minus 1. So 1 over, sorry, it's 10 over 2 to the 2 minus 1. 10 is the width of the interval. And 2 to the n minus 1 is 3, so you're only 3.33 for that reason. Yeah. So you just convince yourself after playing with it a little bit that, yeah, this works, and it probably works. If we use 3 bits, we'll have higher resolution. 4 bits will have even higher resolution, 5 bits higher, 10 bits. At some point, you say, you know what, further resolution is no longer required, right? And that's, again, the art and science of genetic algorithms. That if you, when you're playing with it, let's say if you have a variable that's dollar amounts, you say, okay, I'm going to work with $5 amounts. Okay, then you don't need to have very high resolution. You find the resolution that'll work for you. Similarly, you have many times in manufacturing or design your standardized parts. You can buy 10 mm bolt, you can buy a 9 mm bolt, you can buy an 8 mm bolt, and so on and so forth. So you make sure that your resolution matches that. There's no 9.5 mm. It'll be very difficult to procure something like that. So you say, okay, let's have the resolution not be further, because anytime you increase the resolution here, your chromosome becomes larger. All steps of mutation and crossover, they all become longer, and your computational effort is now being wasted in calculating things that are not even that value. Okay, so coming back to the simple mathematical problem we have 2 variables, x and y, and then we initially randomly generated these chromosomes, right? So first one is basically 1 0 0 1 0 and 0 1 0 0 0, and then the corresponding x and y values within that interval is 0.8065, negative 2.494, and objective function value is 9.32. Okay. So these are just randomly generated solutions. Just a couple of things to note here. The best solution is solution number 2 with the objective function value of 7.071. Oh, sorry, 7.701. And let's see how it can proceed finding the correct solution.
So are the values of x and y randomly generated?
Huh?
Are the values of this x and y randomly generated?
Initial population is almost random.
Okay.
If you had a good solution, you can seed the initial population with it, but initially you generate randomly. So again, the thing with optimization is in the feasible set, you don't know where the solution could be, right? So you randomly generate, even for classical algorithms, like gradient based, or you will give the initial guess. But let's start here. Let's see where we go. In genetic algorithms, you get many initial guesses. And one thing that is automatically taken into account in this implementation of genetic algorithms is that the solution is going to lie. You don't have to worry about x being less than the minimum amount, lower limit, and y being over the upper limit, because that's how you scale it, right? So when you create these chromosomes, when you map it, it will only map to -5 and 5, right? So your upper and lower bounds are automatically taken care of in this case. So here's the progression of the solution. So I just wrote a simple math code that takes those initial solutions, implements crossover, selection, and mutation, and then finds the solution after that. And then I think my population size was only 5. Okay, so only 5 here together. And you see here that the best value is obviously decreasing over time. After about 90 generations, you see that we get a solution that's -155 or something like that. And then the average value also goes down. Now, in genetic algorithms, oftentimes you will see non-monotonic improvement, right? Things can get worse sometimes if you don't have elitism. Okay. So and that's okay, because maybe when you see that the dotted line moves up, is when it's exploring, it's trying to find other regions where you could find a good solution. So it really helps create a lot of intuition towards engineering problems. And then the other thing is that when you're looking at progression of solutions, sometimes it's better to look at the average objective function value of all the solutions in the population as opposed to the best, because here the best is moving very well. Sometimes you can get lucky and you find the best solution right at the beginning, and then you see the best solution didn't move at all, even though the genetic algorithm was working. So an average value is a good indicator of whether the solution is progressing. Yes. So if you see after many generations that the average value has started leveling out, that's maybe the time to stop. Okay. Okay, so now just some basic parameters that was used in the optimization. So the crossover probability was set to 0.7. The mutation probability was 0.2. Just two numbers that I use. People sometimes play around with these for complex problems. Generally, they start getting an idea of what number we should use. We ran it for 90 generations, and the optimal solution was -5, -2.742, and the objective value is -130.19. Just to compare this with randomly generated solution, we had 7, and then we got to -130. So we made a substantial improvement in the optimal solution, the objective function, so that's good. If you look at the true optimum, so this problem can also be solved using calculus, right? So we can compare how did we do compared to the actual true solution, which is -5 and -2.5. You see that, yeah, the x values or x and y values are, well, x is pretty close, but y is somewhat far. But you don't see a lot of improvement in the objective function. Okay, so that's good. That basically tells us that we found a solution. A couple of things to notice here is that GAs may never get to 130.25. Okay, they have this variation built into them. So they can dance around value forever. Gradient-based methods, if they can get near the objective function, they will find it. They are very good when they're close to the actual output. The other, and probably more important things to know, is that, yes, one thing to say that objective functions are pretty similar, but you should also focus on what happened to the actual design, right? So we sometimes think about, yeah, we want to minimize this, so we have this design. But it's the design that you build. This is what you have to build, like the dimensions and the materials and things like that. You don't want too much variation from that. So let's say somebody says that I can get from -130.19 to -130.25, but you have to change pretty much everything that you're doing. So, well, okay, but maybe it's not worth it. Even though it's better, changeover cost may not be justified. So you also look at how robust the X values are in different solutions. I'm just trying to add some discussions relevant to system engineering. Okay, so the next one is GIAN simulated annealing. This came out in 1983. It's a heuristic for finding decent solutions to an application. Similar to other heuristics, it may not find the best solution, but it can find close to good solutions, right? So this is provided by the annealing process used in metallurgy. We perturb a solution, we take a solution, we move it to add variation just like we would in any other heuristic. And then we accept a new solution with a given probability. Okay? So the probability that it will accept a new solution depends on two factors: fitness and temperature. So many ways to implement these rules. Heuristics are always free-for-all type algorithms where your objective more or less is to find a solution. Okay, so you focus on how can I use optimization algorithms to find solutions as opposed to using the best possible method for a specific set of rules. So one common way you do is that find the difference between the objective of the current solution and the next solution and combine it with the temperature value. So the thing with simulated annealing is that it can allow movements to inferior solutions to avoid getting stuck in a poor local position. Right? So exploration sometimes is value. So let's say delta C is the objective function value difference between mu and old. F has to be minimized, but delta C greater than 0 will be accepted if this condition is true, right? So on the left-hand side, we have a uniformly distributed random variable and T is the temperature.
So what does delta C stands here?
The difference between the objective function value of the old solution and the new solution.
Okay.
Right? So now here we just show you what we do over time, right? Over time, we decrease the temperature. Okay. If we decrease the temperature, we have this function exponential e to the negative delta C over T. Okay. So in the beginning, we may select a solution with some probability. With higher, we can select inferior solutions with higher probability in the beginning. As temperature increases or decreases rather with time, we will not select those solutions as readily. Okay. So delta C here is f x nu minus x old. If x nu is less than x old, means that the new solution is better, then C is
greater. I mean, the delta C will be greater, right?
The delta C will be negative or positive.
Positive.
If x nu.
If x nu is better,
yeah, then delta C should be positive.
If x nu is better than delta C is negative. In optimization, we minimize things. Right? So which if x nu is a better solution, then fx nu is smaller value than fx old, means delta C is negative. Okay. So if we come here, we see that if delta C is negative, now we have a positive in the exponent. E to a positive number will always be greater than 1. Okay. If e to the positive number is always greater than 1, a better solution is always accepted. Okay, but we may also accept inferior solutions. That's the whole idea here. And the probability of accepting inferior solutions is proportional or is affected by it. If it's very bad, the probability goes down. Right? So some consideration: the initial temperature must be high. Right? So we initially give a high acceptance rate. Even bad solutions are accepted. Then you have a cooling schedule, so you can say, okay, every step we will decrease the temperature by some factor of alpha. So again, there's many ways to implement these rules. How to decrease temperature over time. You can have a slow cooling schedule. You can have a fast cooling schedule. You can so on and so forth. And you go from there. So basically, this is again another algorithm that is easy to implement. You don't have to do too much to implement these algorithms. And then actually, I could have shown maybe in the next lecture, I'll bring back some of the slides that I have that actually show this. I mean, it requires me to run MATLAB codes to demonstration of how inferior solutions are getting and then how you get to a good solution. So I can show that in the next class, in the beginning of next class. Okay, so and finally, some more conceptual things, multi-attribute optimization. Hopefully things are coming together now that we intentionally studied multi-attribute decision-making because decision-making and optimization go hand in hand, right? Decisions rarely involve single attributes. You've heard this before. You answer questions like, how much should I pay extra for design that simultaneously reduces cost by 10% and increases reliability by 30%? We need to know the trade-off behavior, and in addition to the preference order over each ad, right? And the preferences for risk. So how to optimize systems whose performance is measured over multiple parameters? Well, if preference information is available, we can just perform optimization with the utility function as objective. There's a single objective optimization problem because we have the utility function. Otherwise, we can generate the Pareto front over all the attributes, and the decision maker selects the solution most desirable to them. Okay, so we can actually completely bypass finding the utility function. So I'll give a brief introduction to multi-objective genetic algorithms. So in some ways, the golden era for genetic algorithms came with the advent of what we call MOGAs, or multi-objective genetic algorithms. Because this was a problem in engineering, this was a problem in decision analysis, this was a problem in optimization, that we didn't fully know how to combine objectives into one that will give acceptable solutions in practice. So again, a lot of things in practice, right? That people will accept, people like, and are feasible. So genetic algorithms came out as the way they can do that. We can do that. So you've already seen this, right? That we can always make this decision when we know the preference order, that which solution is better, which solution is worse, in what quadrant. So if we have dominance, we can get rid of the dominated solution. If we find a solution that dominates our current solution, we move there. Okay? Reject that, accept this, and we can now come up with what's called the Pareto front. Pareto front is the limit that nature puts. You cannot simultaneously improve these two objectives. The only way to improve one objective is to compromise the other to some extent. Okay. So, brief introduction to MOGAs. Right, so first, the idea is that you use this, what we call non-dominated sorting, find a Pareto front. And then if we find a Pareto front, there was a lot of effort being expended in finding a well-distributed Pareto front. Okay? So which is better, do you think, on the left and right solutions of the Pareto fronts? That is better. Why is it better?
Because we have kind of boundary. In right, we don't have the boundary.
We still have the boundary, we're just missing some solutions, right? So we have a clumping. We have a lot of solutions sitting together, which are very similar to each other in objectives. And then we are missing this region. So maybe somebody will say, you know what, I would really love if you could improve this attribute, and then the other hand, we don't have a solution there, right? So a lot of effort was spent on finding well-distributed Pareto fronts. So like that. So one algorithm that came out and was very successful was called NSGA2. Actually, its predecessor, NSGA, existed in the 90s, which used dominated sorting, but then it required a parameter, right? And people don't like having to specify parameters in objective. I mean, sometimes we have to, for heuristics, we have to, but we try to minimize those, okay? Because we want methods that work in all general problems, don't require constant intervention. So NSGA2 answered that question. It was the first test for dominance, and then applies an algorithm to ensure that points are identified on Pareto fronts are well distributed. Right. So it found, if I remember correctly, it would apply dominance, because dominance obviously wins. And then if it had a choice between solutions that are close to already existing ones or far away from already existing ones, you prefer the ones that are far away from existing ones, right? You force the solutions to spread out. Actually, during my PhD, I wrote my own NSGA2, and I'll show results of that in the next class. So here's the paper. So what we call one of watershed moments in our multi-objective optimization. Strongly recommend that you go over this one. A fast and elitist multi-objective genetic algorithm, LSGAT. Okay, so just to close this out, we have a few examples here. So you've seen this Venturi many times over. I did a small optimization of a subsystem Venturi, just the Venturi, right? Now, what if you had to optimize the entire system? You know from your multi-objective optimization understanding, the objective cannot just be performance because you will now, the system might cost too much or maybe expensive to manufacture. The objective cannot just be cost because then you optimize other things. Again, reliability and performance are sort of go hand in hand. If you increase reliability too much, you also increase the cost. And trying to connect it with our initial few discussions, I think the first and the second lecture that I gave here was that many systems engineering practitioners argue the firm's objective should be to make profit. Okay, so how do we convert the performance of the Venturi's cover into profit?
I think we have to define a utility function. How much we like performance, how much we like profit, and how reliable we is.
Our utility function or the customers? Because we're trying to make profit.
So like the customer's utility function.
Right? So one of the things that we say is that, so this is looking at demand. Okay, so let me just break the suspense here. We're looking at demand in this case. Profit is a function of other metrics we saw, for example, I read that. One needs a good amount of demand to be able to predict sales and hence profit in the system metrics, right? So our utility, as the manufacturer's utility, will be utility function, will be a function of how much, what is a brand image, how much, well, what is a profit, what is a brand image, and so on and so forth, right? A customer has a utility, but one customer has a utility function, another customer has a utility function. It's hard to reconcile utility functions with multiple decision makers. So we, in this case, are using just a demand. Okay? So here's just this is just a notional example. So we should not get too carried away in one of these things, whether this is the exact model or not. So, but let's say that the customer cares about, and we've done our analysis, we've done our focus groups, and so on and so forth, people who use these things, let's say, and then we found a demand function of sorts where we said that, people, this is not a product that, that is the main product. People are running lab experiments. They're just using the scrubber so it does their job, right? So we can say, okay, they're interested in mean time to failure in days. Those are the attributes that customers care about. If you remember that, that's what we talked about. And the price of each unit, right? So if you give me this and it works, I'm happy, right? And this is just a notional relationship, so don't worry about where it came from. It just makes a little bit of sense that demand will be higher if mean time to failure is higher and the price is lower. Okay? Based on a profit margin of 35% per cover. So this is a profit margin, and then a profit rather. Then we start building this system model and we say, okay, well, mean time to failure, how do you find mean time to failure? Well, we do some experiments and we do some analysis and we say that the experiments show that the increase in flow rate in GPM decreases the mean time to failure, right? The system barely runs, it will not fail. If you use flow rate, maybe it erodes the nozzle, maybe it causes other issues, maybe the motor fails because you're trying to run a high flow rate. So here's some notional example, right? So the price equals manufacturing cost plus profit margin. 35% cost is equal to fixed cost of 15,000 plus a function of flow rate, because increasing flow rate increases the rating of the motor and that as valid components, right? So if you say I'm going to run higher flow rate, you need to be more expensive motor and more, let's say, more sturdier components. Okay, so these are all notional relationships. We're just gonna assume that this is correct. And then finally, the manufacturer wants to guarantee 8 inches of negative pressure. So we say that this should be true. If you remember last few slides, we had, last few lectures, we said we have fit a function to that, right? So now we're thinking more system level. I am a manufacturer. I want to maximize profit. To have maximized profit, I need a demand function. Demand function is customers, basically something that I find by talking to customers. Customers care about mean time to failure and price, right? My price is my cost plus some profit margin. So I want to make sure that my profit's higher or whatever. And then it has to have basic functionality. So you can say that customers care about mean time to failure and they care about price, but they will not buy it if you don't give them any performance, right? Which is, let's say in this case, 8 inches of negative pressure. You could just say that I'm going to use 5 inches when I use my earlier example, but you don't want to sell it to that one customer. You don't maybe sell it to multiple customers. So these are just constraints that are coming from different requirements that different teams have put on. Okay. So we write the optimization problem. We say minimize Q of X, which is my profit, if I remember correctly, right? Q is my profit, total profit. Okay. Minimize the negative of profit. So we're maximizing profit. This is a common trick we'll use constantly, that if you are maximizing something, we'll put a negative sign in front of it. Where X is depth of the nozzle and the flow rate. Because from the depth of the nozzle, we can, at the flow rate, we can calculate the mean time to failure. And then price that we select is cost times 1.35, which you can sell the customer. And cost is 15,000, which is the fixed cost plus some function of the flow rate, because we said that higher flow rate requires us to build a sturdier system. Okay? Subject to that these variables are non-negative. And the negative pressure that we generate exceeds a certain amount. So to understand this optimization problem in detail, I mean, we've already gone through it. Maximize profit so that the system functions, makes us money, and there's some relationships that are built in that if you select X, which is your nozzle position and flow rate, you affect the other variables like so, and you also want to make sure that your negative pressure is to a certain point, so that becomes the constraint in this case. Okay, so we already talked about Excel solver in the earlier lecture. I guess it was this lecture, and then I will leave this problem as an exercise for you. Play with this, and you will see this in your slides that you get. So solve it using MATLAB or Excel or whatever, and then you find what flow rate we should use and what nozzle position we should use for this to work. And some things to understand, when we did an unconstrained optimization, just like maximize the negative pressure generated, we found a different solution than this, right? This is a constrained solution. This has more layers to it. You would love to create a higher negative pressure. Higher negative pressure requires you to increase the flow rate. Increasing the flow rate has a negative effect that it number one, increases the cost of the product, which decreases demand, right? Also, it affects negatively the mean time to failure of this. We have to do that, but we don't do it because, so simultaneously addressing all these requirements is what optimization allows us to do, right? It took care of all those things and the models that we have. Let's see if there's anything else to say here. I think we're good. Just to reiterate that these are notional relationships, you will, even if you don't have actual mathematical models, you can still collect data and create functions. So this actually, the very last constraint was done using just data collection, right? We didn't have a physical model of that, but we empirically determined that this is a relationship between flow rate, nozzle position, and negative pressure that you generate. Okay. So that just brings home the whole thing about the Venturi's problem. The next example that I can briefly go over. So this is taken from this publication here, that we have a welded beam with these characteristics, and you're trying to minimize the cost and the deflection of the beam, right? So this problem again has been taken from this publication, and I'm just trying to do a demonstration of how we can use MATLAB to set something like this up. Okay, so a bunch of constraints, dimensional constraints, bunch of stress strain type constraints, and what I do is I try to follow a systematic approach where I build the model incrementally. So what I try to do, and again, this is something that you can have your own method of setting up optimization problems. I write a main code where I determine or define my starting points, upper and lower bounds, and I call the admin con function MATLAB, right? And for each constraint, I write a separate function. You don't have to, you can calculate all constraints together. But this one does the first constraint, this one does the second constraint, this one does the third constraint, this one does the fourth constraint. And then here I put them all together, right? So I say, this is the set of nonlinear constraints that I have. H, L, T, and V are the design variables. I just rename them as, I just rename the design variables in X as H, L, T, and V so that I don't have any errors. I don't really need to do it here, but that's okay. It's just grab them from both codes. And then G basically calls all those constraint functions and puts them together. Okay. And then H is nothing because there's no equality in things. Okay. And MATLAB understands this. So if you give, for example, in the main file, you look at the very end, you say non-LCON. That's just the format of how AppNetCon works. AppNetCon takes what is your objective function, you give the file name of the objective function, which should be a function that accepts the x value and return the objective function value. What is the x0, which is starting point? You can select any starting point, and then you have a bunch of linear equality constraints, linear equality constraints, if I remember correctly, and then you have lower bound and upper bound for all the design variables. Which is 0 and 100, and then you tell it the name of where the nonlinear constraint lives. Okay, so AppNetCon is used for nonlinear optimization. So we keep going, and then we have non-LCON, puts all this together, and then objective function 1 and objective function 2 are here. Remember, there was one objective function which had to do with cost, so there's no objective function that had to do with deflection. Okay, so, and that's that. Now, if I come back here, we have objective function file, which I don't seem to have here. I do. So objective function file, but when you go to objective function file, it calls the objective function 1 and objective function 2 files, right? So I had objective function 1, which is, I think, cost. Objective function 2, let me just make sure that I don't say something incorrect. Objective function 1 is cost, and objective function 2 is deflection. So I have two objectives. What can I do with the multi-objective optimization problem?
So first you have to convert the multi-objective into a single objective function.
We don't necessarily have to do that. We can just do Pareto from these, right? So there's a couple of ways I could have proceeded. I could have made it into a single objective, like you said, or I could have just let it be and find the Pareto front for cost and deflection. That's one way to do that. Okay.
So, but then we have to do like for both the objectives, right?
Yeah, then you do multi-objective optimization, which creates a richer paradigm. Now you have a set of all the good solutions, and people with different preferences can select one that they want. Okay, The other solution is the utility function solution. That's what I've done here. I take, if you look at line 15 and 16, what I do is that I take C, which comes from my objective function 1 file. I just give it X and I can get it back. Get back the objective 1 value, which is cost. I give objective function 2 file X and get the deflection back. And then I use exponential single attribute utility functions, U1 and U2, over those. So I would have had to assess those. So what I did here is that I put all of what you learned so far into one. To say, okay, let's say that I wanted to minimize cost and deflection simultaneously. What is your preference, right? And you can think of it realistically. Okay, what is the beam used for? Somebody will say that, okay, maybe this beam is something that people want. So you want to make sure that it's sturdy, right? Deflection is, but you don't want to spend too much money building it too. So there's a trade-off. So you build a active utility function. Anybody remember what kind of multi-attribute utility function we're using here?
What kind of multi-attribute
utility function we're using here? Multilinear, right? So for two attributes, you can write it like this. If you remember 1 over k times the product of kk1, u1 plus 1 minus 1. That utility function for two attributes, you can write it like this. Okay. So it has u1, it has u2, and then it has 1 minus k times u1 times u2. Means that it's not just a linear sum of the utilities of the attributes. It also looks at the interaction terms, okay, the u1 times u2. K1 and K2 you will assess like we discussed last time. So basically that measures your relative disinclination. Somebody will say, yeah, just give me something cheap. I don't care too much about deflection. Somebody else might say, no, I want a sturdy beam, even if it's more expensive. So people's different preferences could be represented in this fashion. The single attribute utility functions are exponential, as you can see. And we solve this optimization problem. Now we have done an overarching optimization using multi-objective optimization, using our knowledge of optimization, using our knowledge of decision making to optimize the system. Let's see if there's anything else I wanted to say here. Yes. So if we solve this problem as a multi-objective optimization problem where I did not do this utility function step, I just simultaneously minimize the two objectives where I get a breakable. And I do a solution, solve this problem using the utility function like I do here. Will this solution be found on the breakable?
Yes, so it will be one of the solutions.
Yeah, it will be one of the solutions, but it will be one of the solutions, right? So the breakable is richer that way. But if you're 100% sure that this is the actual utility function, might as well just use it, right? So if you have it, then you can use it. But you don't have it, you use greater part. Okay, all right. So I think that's the last slide I had. Oh yeah, so then just come back to the main file. You just come here and you run it, and then it calls the functions in the order that it needs to, and then finds its solution. Then that covers this lecture.
So if we have we can do the convex optimization based on heuristic, right? Heuristic doesn't give the